hopefully are looking at here. Yeah, looks like we're doing good. Yeah. We're going to be working on section 5.4 today. We're going to be looking at indefinite integrals. Actually, we're going to be looking at indefinite integrals and definite integrals, and a guy called the net change theorem, which actually isn't much of a theorem because we already know the answer. We just never gave it a name. Now, if you notice, my little picture is a little bit different than usual. I tend to draw the whole curve above the x-axis because it's just easier at the beginning to have that way around. But essentially, if you were finding the area under the curve from a to b of some function, it's still the antiderivative at b, take away the antiderivative of a. But what we have to be aware of is that it's the area under a curve. It's not the physical area, although sometimes both match. We've done this before. Isn't this area here positive and this little bit over here is positive? But isn't this area here, the one with all the little dots on it, wouldn't that actually be a negative number? Right. So that when you get the integral from a to b, right, the area under the curve from a to b, couldn't this answer, in certain circumstances, be positive, it could be negative, or it could even be zero? And so the net change theorem is basically just saying what we kind of already take into account, that what we're getting here is not the physical area. The physical area is a positive number. We're getting the net area, or as they like to prefer to call it, the net change. And so that number could be positive, that number could be negative, or it could even be zero. And it's okay, no matter what it is. Right. So we kind of talked about that earlier, didn't we? All that we've got now is a name for it. And the net change theorem says that when you find this integral, you're not getting the physical area, you're getting the difference between the positive and the negative. You're getting, if you want, the net area, which is actually a name I prefer. Analogy. Do you know how like you get your gross income and your net income or something, like one's the big one, one's, it's kind of like that kind of idea. Apart from the fact that that's all it is, we don't need to spend a lot more time thinking about it, because really what we're going to do is lots and lots and lots of practice at finding integrals, because the more you find, the better you get, right? It's just a matter of practice makes perfect, right? So here goes, I'm getting this up and running, and we're going to look at different groups of questions that have something in common. So the first thing I'm going to do is just a kind of warm-up one, but we're going to look at integrals that use trig functions. So I'm going to use trig functions. These are the guys I can integrate, right? These are the only guys that we can really deal with. Right? So let's pick a baby one to start with. The integral of 3 sine x plus 2 secant squared x. If you gave me that one to do, I would just say, if you want to find the antiderivative of sine, it's a negative cosine. So that's negative 3 cosines. A secant squared, well, the antiderivative of that is a tan, so 2 secant squareds gives me 2 tans. And since this one is an indefinite integral, I'll put a big plus c. Are we happy about that question? It's just a matter of knowing what the antiderivatives are and using them. Go with that? Now, I'm not doing it because it just takes up too much time, but suppose that was 0 and this was pi, just for argument's sake. Wouldn't you just remove the plus c and evaluate this when x is pi, evaluate this when x is 0 and subtract the 2, right? And you get an answer, whatever it would be. Well, that was a nice integral involving trig functions that didn't really have that much going on, right? Nothing too weird or wonderful. So let's do some weird and wonderful combinations now. Let's do the integral of 3 plus 2 tan squared theta d theta. Are we good? Now, you might say, antiderivative of this is 3 theta. Antiderivative of this is, oh, you're not in my list. And that's why we need to do trig identities. So 142, you have got to know some of the basic trig relationships that allow you to turn something into something else. And I am going to take that tan squared and I'm going to turn it into something else that ends up being secant squared, because I know how to get the integral of secant squared. So this is definitely going to test your memory, and well done if you can actually tell me what this is. Tell me what tan squared is in terms of secant, Sarah. Sabrina?
Tan squared plus 1. Full confession, I've just got really good notes from last year.
Are you sure it's tan squared plus 1?
Yes.
Are you absolutely sure it's tan squared plus 1?
It's what I've got.
No, what you've just told me is secant squared theta is tan squared theta plus 1. I don't want to know what secant squared theta is. I want to know what tan squared theta is. So look at your good notes again.
Minus 1.
Yeah. Now, out of these two, that one isn't any use to you. Because if you tell me what secant squared is, won't I just go over here and write the answer? I don't need to change secant squared, right? And I'm writing that down. I should have stopped, but my brain was too busy interested in the answer. So tan squared can be written as secant squared theta take away 1. Then what I'm going to do is distribute the 2's. And then I'm going to get this guy. So the original question, we didn't know how to do it because we don't know the antiderivative of tan squared. After a few lines of tweaking it and doing it, we got this guy. But this guy is good because 1 has an antiderivative, in this case theta, and isn't secant squared tan, so 2 secant squareds has an antiderivative of 2 tan plus a c. Are we comfortable about how that one was done? Now, the good news is that because in your test, you will have pieces of paper where you will write down things like, yeah, I better write down that tan squared is secant squared theta minus 1, right? So that if I ever need to change it, it's there, right? That would be the kind of thing. But it's even better if you can memorize it, because then it's quicker. Now, what I'm going to do is kind of change tack for a few seconds, because one of my students from the other class shared, which was very nice of them. If I can find it. Here? No? Okay. Went and shared his cheat sheet. Basically just his formula sheet. I don't want that. What's that doing now? Take me a few seconds and then I'll be in and you can have a look at it. Okay, I think we're ready for it. Go here. Right, I'll switch over, show you where it is. You might want to print this out. You might have a better version of your own, that's fine. But it's just a little resource for you. Here we go. And while I'm here, you know, if you click on this guy, and then you go to week 2, you see this is where our videos, in case you want to go over something. Let's go back and look at his trig formula sheet. There is more on this sheet than you will ever need to use, but Better having more than not enough, right? So you remember SOHCAHTOA and this stuff? We'll actually use that in a totally different section a lot later. Domains, I don't think you need to worry about them. And various combinations of what you can call these guys. Here's the good stuff. You see conversions. And you see that one there has the tan squared plus 1 equals secant squared. But if you rearrange that one, isn't tan squared secant squared minus 1? Right, and that's the one we just used. So any kind of identity that you're looking for that would help you, that's where it would come from. So let's return now to another trig question. We need to figure out a different way to write that, because the only things that can work have to be in this list of 5 choices, right? There are not an awful lot of choices here, right? So, does anybody know a different way of writing the sine of 2x? It's called the double angle formula. Do you know it off the top of your head? The sine of 2x. Do you have a double angle formula anywhere?
2 times sine x times cosine x.
And since there's 2 of them, I'll just double that up to 4 sine x cosine x. So I've made it a little bit uglier, but the benefit is, don't the cosines cancel? And so this becomes that. And isn't that something we know how to integrate? It's negative 4 cosine x's, add a c. Cool. Right, let's look at some more of these guys. Oops. This one is a version of question 34. I can't remember what one that is a version of, but one of your homework questions look like this. But the one I'm about to do is a version of question 34. And it's 5 sine theta plus 5 sine theta tan squared theta. And the whole thing is going to end up being secant squared theta. Now I can imagine superficially you would look at that and say, nah, ain't going to happen. No way in the world that is ever going to turn into anything easy that I could find the antiderivative of, right? But let's try and make it happen anyway and see where it goes. Is there anything you could do algebraically to this expression? Anything as you look at it looks like it might work? Okay. Anything on the top line in particular?
Factor out of 5 sine theta.
I like your thinking. Sometimes you have to just do what your brain tells you and then pause and see what it turns into. Because you might not see the whole picture in one go, but after you do one step, sometimes things become clearer. Do you see anybody on the top line that could be turned into something different and useful? Sabrina is nodding her head, so she definitely sees it. Mia is smiling because she's happy, but I don't know if that means she sees it. And I can't tell because Cassandra's got a mask all over her face. Oh, she's smiling. Okay. Anybody want to tell us then? What could we change here?
The 1 plus tan squared into a secant squared.
And the good news is that doesn't not exactly match the guy on the bottom. In a kind of sort of a way, wouldn't it have to be secant squared even if we didn't know it was secant squared? Yeah, because that's the guy that's causing the major trouble, right? That thing. And it is in fact that. And so what you're left with is just that guy, who happens to be -5 cosines. So we are doing integrals here. Do you see that the problem is that we're not just getting ones where you know the guy and you know the answer? Aren't we getting questions now where we have to work on it quite a lot of the time? The guy they give me isn't actually the guy I end up using, right? I have to be able to take things and make them look different. You know, take things and change them. And once they're different, then I could, you know, start using the standard integrals, as they are called. I'm putting this one in as a trick question. I do not need to do anything to that question, which is why it's a trick question. It looks like I need to change it into something else like all the other last three were, but I don't. What's the answer to that?
Negative cosecant of t plus c.
Yeah. It's a standard integral. There are some integrals we just say, look, this is the answer, trust me, right? And so if you get one like that, well, you always take the easy route and not start looking for weird trig identities and spend half an hour, you know, because what would probably happen is it would get uglier and uglier as you start trying to play about with it and change any things. So instead of getting closer to the answer, you get further away. So you do have to know. So I guess, well, how would I look at that in my brain? I would look at the question first and I would say, are you one of these? And if the answer is yes, I say, thank you. I write down the answer and I go to the next question. If you are not one of these, then shouldn't I think about, okay, what can we do with this trig expression to turn it into something else so that it does become at least one of these? So that would be my goal, right? So don't get caught up, because sometimes, I guess what's the phrase I'm looking for? Do you know, sometimes you can overthink things and you start making them harder than they are. Because the last 4 questions were really hard and you had to do stuff. And then question 5 comes along and you're still in that, you need to change thing mode. And that's what happens here, that sometimes a question, as late as question 36 is dead easy. My next group of puzzles, I'm going to describe them as puzzles that involve factoring. So to be able to get the answer, you end up having to factor things. So let's give you an example of what that might look like. Now, if that guy was just over 2t, right? I would do it a totally different way. Wouldn't I break it into 3 fractions over t or multiply by t to the -1, right? Whatever I felt like doing, right? That +2 changes the story completely. That technique that I mentioned a few seconds ago won't work. But what will work is factoring. Do you see something nice happening here? And so this fella actually is that fella. And that's a power rule. See how nice it looks after the factoring? How about this one? This one is a version of 37. I'll take a volunteer here. Factor something for me.
The bottom is a difference of two squares.
Correct. It's a little bit unusual as a difference of two squares, but that's what it would be. You agree, Matthew? T squared plus 1, t squared minus 1, right? Of course, I know I could factor the top, but you see, I'm actually not going to, because nice cancel. And you look at this guy. And then if you're not careful, you start thinking you've done something wrong and you can't get the answer. But isn't that just a version of this fella? And so what you're looking at is an inverse tan of t. Typically, this question would have a plus c, but let's just, for argument's sake, that it was 0 to 1. So when I got to this line, I would do that guy, right? So I wouldn't have my plus c, I would have that. And then I would have inverse tan of 1, take away inverse tan of 0. I'll do that shortcut again. You know, when you do inverse sines, inverse coses, inverse tans, you can actually let your calculator do most of the hard work. Make sure you're in degrees, which we are. And inverse tan of 1 first. Inverse tan of 1 is 45 degrees. And then turn that into radians. Hopefully you know how to do that. 45 degrees. And that guy is 0. So there's your answer. Looking good. So factoring is a strategy that can certainly work. If you're going to do factoring, would you agree it's almost always going to be a fraction? And then the guy in the bottom disappears because it's got the same guy at the top. So if you recognize it's going to be a factoring question, can you pretty much guarantee that whatever's on the bottom, that's going to be one of the two factors on the top? You kind of know that is the way it's going to work out, and that's exactly what it is. Okay, that's enough factoring. Let's look at, oh darn it, there's so many choices there. Right. No particular rhyme or reason to these, I'm just randomly picking problems. Suppose I had to do this guy. Which happens to be a version of question 24. I need a strategy for how I'm going to get these guys to look like somebody over here, right? A standard integral. What do I do? How do I rewrite? How do I rewrite 1 over x squared?
You would change it over to x to the -2, put on the top.
I agree. And for the same reason, wouldn't you call that -3? If it was 1 over the square root of x, wouldn't I call it x to the -1/2? You know, for example. We've seen those before. Right, power rule. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Haven't talked to any style points. Let's talk style points. That needs some style points done on it, doesn't it? What would this first one become? How would I write that?
1 over x.
Okay. And 3 over x squared, and everybody's happy. What about this problem, which is just right underneath it? There are so many different things that could happen I can't cover every possible, we don't have time, thing that could happen. So all I can do is little snapshots of, you know, certain kind of features that you should be looking for. Would you agree this guy has a problem? And so we got to fix that problem. And algebra is going to be our friend, right? It's going to be the way to do that. Any suggestions for how this one would get fixed?
Looks like factoring one.
Oh, you mean like the top could factor? Is that what you're thinking, Sabina?
It
Yeah.
was, and now I'm not.
Not so sure now. Isn't the big problem that if you factored it, it doesn't have a common factor of x? Right. So, okay, that is a good strategy. If that had said x plus 1 in the bottom, I'd be more likely to do what you just said. But it only has x in the bottom, so I'm going to go a different way. How are we going to go?
Multiply the top by x to the power of -1.
Do you recollect us doing a question, something like that before? Oops, that's a 1. You remember? I mean, it's all to do with experience. The only reason I'm pretty good at anything in math is because I've been doing it for 40 odd years. So I've probably seen almost everything that you're likely to see in a calculus textbook, right? Occasionally I get caught out because I'm old. So that's just experience. So what does experience mean? It just means I've done literally thousands of integrals in my life. So by the time you've done 1,000, don't you just get used to certain things and you see them, right? So hopefully you do enough practice. That's what homework is, right? That you'll say, oh, I've done 4 or 5 of them. Yeah, I remember what you do. In this case, you multiply these together, you get 3x. That one's a bit messy, but you get +3 when you're finished. And that one is really ugly at the end. And that one is the one that's causing me trouble. But if I realize that it can be called 1 over x, do you see it's not such a problem anymore? And I'm going to go ... now because we have lots I want to cover, and you know, you could finish that off yourself. Well, let's talk about some. That way I can cover more without physically doing. So I'm going to go to the homework and we're going to just talk through what would be the method, right? We don't need to get too caught up on the details. Are you looking at our homework now? Okay, let's zoom up to the top a little bit and talk about technique. I'm going to make these a bit bigger because I don't know what kind of screen you lot have got. Yeah, hopefully you can see it nice and clearly now. Now, this first one is a one-off question. You say true or false. If someone says the integral of this is that guy, if you wanted to check it, don't you differentiate your answer and should get this guy? I'll take your word for it. It's probably true because it says true, but I wouldn't know that until after I did it. So let's kill that one off. That's the only question that looks like that, so don't read too much into it. Okay, power rule. Yeah, go for the obvious. What about that one? Can we just do it right off the bat? Yeah, full of standard integrals. Okay, what would you do? Don't need the answer, but what would you do to that guy to get him ready so we could integrate? Number 4.
1/7 power and -1/7 power.
Yeah, and then just do the power rule on it, right? The 7th root of x is x to the power of 1/7. Remember fractional powers, radicals become fractional powers. That's what would happen there. Question 5 looks horrendous. It's just actually nice. It just doesn't look nice. Isn't it just the power rule, but with ugly powers? So don't expect your answer to look pretty because it won't. What fractional power is question 6?
X to the power of 9/8.
Right, and would to be a really ugly fraction, but it's a power rule. Would you agree that's just a power rule with the coefficients of 2 7s and 3s, right? So just ugly numbers to work with. Wouldn't you agree that's a nice baby question? power rule without really anything that weird going on. Okay, don't need the answer. What would you do in question 9?
Foil.
Yeah, foil it out and it's a power rule. You recognize that guy because we did it or something like it. You can multiply by x to the -1, or you could split it into 3 fractions. It's the same thing. Power rule, power rule. What on earth is this guy? What's the antiderivative of 7 over x squared plus 1? You don't need to do any algebra. What's the answer?
Isn't that 7 inverse tangent?
7 inverse tangent x's. Oh, I better do this one at the side. This question is easy, yet it's fraught with danger. What do I mean? Right. I don't need to do anything really significant to this. It's not some weird identity or some clever algebra. I just need to find out what its answer is. The antiderivative of e to the x is my friend. I never really screw that one up. This guy here has a problem. The correct answer is 1/7 the natural log of x. The way it is written will generate all sorts of weird wrong answers. This is a wrong answer. It's a natural log of 7x. It is wrong. Oh, when it's 1/7 the natural log is 7x. Different, wrong. So how does this guy become that? Well, you just have to think about it in a slightly artificial way, but I think it helps. Does it look much more like 1/7 log of x now that I've written it this way? It's just a little niggly thing that is easy to screw up. I mean, it's not a hard question, it's just an awkward question, isn't it? What do you do with that 2 or that 7 or whatever it is in the bottom? Just for argument's sake, suppose that was 10, wouldn't the answer just go 10 there? Wouldn't really change much. Okay, now let's return back to this section, see what kind of cool things they still have in store for us, because they do have stuff. Isn't that just a standard integral? Even 7 over x works. Is it for 5 over x, I should say? Isn't the antiderivative 5 over 5 to the power of x all over the natural log of 5? Don't need to do this, but tell me what you should do. How would you tackle 14?
You could distribute the squared to the top and the bottom. And
You
then
should.
foil the top.
Yeah, if you did that, you would get 49 plus 14r plus r squared. And on the bottom, you get an r squared. And wouldn't that be one of those questions where you would then multiply the top by r to the -2 and do your thing? So that's how you would do that one. We've covered that one, or at least one's like it. Remember the secant squared -1 guy? That's where that comes from. We've done ones like, have we done ones like this? Yeah, if you distribute that, right, multiply by secant t, it ends up being 2 standard integrals. Definitely done that one. That's basically just standard integrals. Oh, there is something that I should show you. If you want to do the integral of cosine x, that's just another word for the antiderivative of it. It would look something like this. There's the sine. One day I'll learn to hit the right buttons. There's the sine of x. Plus, well, it's a power rule, plus fraction then 1/14 x squared. And remember to finish with the plus c. Okay, that's nothing special, right? That's an easy thing. So what on earth are all these pictures that come underneath? I want you to imagine that you went to your TI-84 and you typed that guy plus 5, that guy plus 10, that guy plus 15, that guy with no number, and then that guy minus 5 and that guy minus 15. Can you imagine you could have 5 or 6 graphs on your picture, right? Y1, Y2, Y3. If you did that, it would look like that, or it would look like that, or it would look like that, or finally it would look like that, isn't it? Look at your calculator and pick the picture. This is a definite integral, but isn't that a nice power rule? Nothing much going on there. Power rule, more power rules. Okay, hopefully this one's a pretty straightforward one. What would you do in question 23? What would you do in question 23?
You would just FOIL and then power rule.
Yep. Are we getting more? The more of these I do, I want you to eventually say, I'm beginning to get the hang of these. This is what you do in this situation, and that's what you do in this different looking situation. This is FOIL, and then it'd be a power rule. What would happen in question 24 then? Don't overthink it. Sometimes the obvious is what you should do.
I'm into the negative powers, so x to the negative 2, and then 6x to the negative 3.
And then it's a power rule, right? And then remember to do the style points at the end because it'll make your calculations easier. Because in a question like that, I expect the answer is probably going to be a fraction when you're finished. Do you recognize 25 as another one of those where you multiply the top by x to the negative 1, and then it's a power rule? You might have to watch out because I believe you're going to have an x to the negative 1, so you have to rewrite it as 1 over x again. You know, that happens now and again. Would you agree this? Well, I'm not going to. Would you agree in this at all? Tell me what you would do in 26. I was about to tell you. What would you do in 26?
Would you just distribute everything and then find the derivative afterwards?
I think so. If what you say is what I think you're saying. So I would do 5 minus t squared and then multiply everything by t, right? Distribute everything. Won't you end up with a power rule? You imagine what you'd get would be various powers, be a power rule. Again, just a technique. What would you do in 27?
Multiply the top and the bottom by u to the negative 1/2.
Okay, just the top will do. I
Oh, the
know what you
top,
mean.
yeah.
But I know what you mean. It's a power rule when you're finished, right? It'll be various fractions, but it's a power rule. What's the? I don't. The way I phrase this question would be too much of a clue. So let me just say, what's the answer? Not the number answer, but the algebra answer.
Inverse tan.
Yeah, isn't that just 5 inverse tan b's, and then you plug in numbers? What is the answer to that guy? The way I'm phrasing it is that there isn't any algebra. You should be able to just tell me what 5 secant squared y is. What's the antiderivative of 5 secant squared y?
5 tangent y.
right? And then can't you then, you know, do what you need to do after that? Of course, having your unit circle will be handy for that question, because if you plug it into the calculator, you're probably going to get 0.167 or something, and it's not what we need. That one's a thinker. Just tell me the method. How would you work with 30? What you going to do with 30?
Turn them into fractional powers and then distribute the x and power rule.
Yep. Ooh. Interesting. I'm not saying anything. Just tell me, what would you do? That's all I'm saying.
Write it as 1/4 x minus 2 times x to the 1 or -1.
I like your start. I think you overthought the second piece. Couldn't we just call it 2 times 1 over x, and that way it's a log? Right? And if it'd been 2 over x squared or 2 over x cubed, you nailed it. I definitely would have done it now. And isn't that one just obvious? I know the numbers aren't pretty, but isn't that just standard integrals and you get an answer? Standard integral. I know that might not look like a standard integral, but that's actually 3 secant x. So the antiderivative is 5e to the x, take away 3 secant x, and then evaluate the two numbers. Do you recognize 34? We already did that one. What is the antiderivative of that guy? You don't need to factor it or do anything. What's the antiderivative of that guy?
Inverse sin x.
Yeah. Or in this case, R, but I know what you mean. Didn't we do that one? Isn't that just a standard cosecant? Didn't we do that one? That was a nice place. We have finished. Well, I didn't do many of them, but hopefully I've given you enough of a kind of, you know, quick snapshot of what 30 different questions. Can you imagine how good you're going to be when you've done 3,000 of them? Okay, that might take you a few years, but you know, maybe 300 would not be unreasonable by the end of this course, right? That you'll have integrated at least 300 things that you'll be pretty good at, you know, your experience will be up. You'll be pretty good at doing them.